Okay. So yes, thank you for that. So one of the things about going last, of course, is that people before have said so many things that, in a sense, it helps me out because there are things that I don't have to say again, and it also means that I have to struggle a little bit more to stay relevant and make sure that I'm presenting novel information. So I'm going to talk about a project that I and a number of collaborators, you can see the list on the slide here, have been working on for the last 4 years, building a citizen science project that actually tries to couple astrophysics, crowdsourcing, and machine learning. And the project is called UniversityThe. You actually heard it referred to a little bit earlier today. So this is obviously very different than wildlife conservation, but I hope that some of the ideas that we implemented will be of interest to the project that you're planning. But because it is so different, I'm going to start off with a little diversion and explain exactly what this LIGO project is and does. So unlike the very, very interesting projects we've heard that are situated in the context of wildlife in Africa, for example, the project here is based around the LIGO detectors, laser interferometry gravitational wave observatories. And those are looking for evidence from deep, deep outer space, billions of light years, for the convergence of objects like black holes or neutron stars. And so that's what that illustration was. As the two objects orbit each other, they, and this is a prediction of Einstein's general relativity, they actually distort the fabric of space-time. And so you get a phenomena like this, where you can see there's a ripple going out from the objects moving around each other. And as the objects get closer together and they go faster and faster, the waves become more powerful and higher frequency. And remarkably enough, even though these objects are billions of light years away, the gravitational waves spread very efficiently and fill all of the universe and eventually make it to Earth. But when they get here, they're incredibly faint. So they're actually distorting the fabric of space. So you can see that little green blob going by, and literally, space gets a little bit shorter in one direction and a little bit longer in the other direction as the wave goes fast. But it's incredibly faint. In order to be able to detect it, you need an extremely sensitive detector, and LIGO has two of them. Each one is an L 4 kilometers on a side. There's one in the deserts of Washington, which is Hanford, Washington State in the United States, another in the pine woods of Louisiana, also in the United States. There are also detectors in Japan, in Italy, outside of Pisa. They're building one in India as well. And remarkably enough, just over 6 years ago now, just under 6 years ago now, the first detection of a gravitational wave event was made, September 14th. I remember that date because we were having the kickoff meeting for UniversityThe a couple of days afterwards, and my colleagues were extremely distracted. They kept getting texts, jumping up, running out of the room, and they could not tell us why. It wasn't until some months later that it was publicly announced, and they had to say what had happened. And you can see the waveform here going past and getting, as you can see, higher in frequency and more intense. It's also shown here in a spectrograph view, which I'll explain a little bit. I'm just really quickly going to explain how it works because it's relevant to what our project does. So as I mentioned, it's these arms 4 kilometers on a side. And what happens is a beam of laser light comes in, it gets split, it goes down the two arms, bounces off a mirror, returns, and the system is very finely tuned so that when the wave comes back and is merged, it's in opposition. You can see how the waves cancel each other out. But then when a gravitational wave comes along and it shifts the length of those arms by a little bit, that wave goes in and out of phase, and so you get a brightening and a darkening. And so that's what the signal is that's being detected. Of course, the actual one is a lot more complicated. I'm not going to go into those details. But the complication is relevant for what UniversityThe is about, which is helping to improve the detectors. Because being so sensitive, the detectors actually not only detect the signal, and so for example, here is a signal you can see very faint in the background. What this is showing is the spectrograph. So we have frequency on the y-axis, we have time on the x-axis, and then the intensity of the signal is represented by the colors. So blue being low intensity, yellow being the highest intensity. So here's our beautiful astrophysical signal coming in, gradually going up in pitch as the objects are getting closer and closer. And right in the middle of it, we have this noise event. So you can see just a big jarring signal, very, very intense, covering all the frequencies, wiping out the signal. So these are what are known as glitches. So glitches are transient non-Gaussian noise. They can be instrumental, that is to say, part of the detector, or they can happen because of nature from the environment. Apparently, the detector is powerful enough, sensitive enough that during a storm, when the waves are crashing on the ocean, which is hundreds of kilometers away, it actually shows up in the detector. And there are a lot of them. And they change as the detector changes. The detector is sort of constantly being upgraded. And as you can see, they contribute to the noise background, and they actually do get in the way of being able to detect signals and do other kinds of studies. Some of them are understood. Whoops. Like these ones come from particular things that are known, but this particular kind of glitch here called a blip is extremely common. They happen every, several times a minute, and it is at this moment unknown what the cause is. So what the scientists who develop the detector need is a nice data set of the glitches when they happen in time that they can use to guide their searches for the cause, looking for correlations between the glitches and other events, which is where our citizen science project comes in. So Gravity Spy, it's actually built on the Zooniverse platform using the project builder tool that was mentioned earlier. Asks the volunteers to look at a particular image and to classify it into one of the known kinds of glitches, of which there are currently about 22. It launched October 2016. The data is a little bit out of date, but so far we've had 21,500 registered users, a little bit more than that actually, who've done 3.4 million classifications. And then just as was mentioned earlier, you look for consensus amongst the classifications and use those to determine the type. However, a novelty is the way it incorporates machine learning. As far as I know, we're not the only Zooniverse project to do that, but I think we're one of the first. And so what we've done is to train a machine learning algorithm on data that was classified by the LIGO scientists. And we use that to do an initial classification to be able to sort the glitches. And then, and this part actually doesn't work quite as well as we would like, to take the glitches that have been analyzed by the volunteers, use them to improve the machine learning. So the overall workflow looks something like this. We get the glitches from LIGO. They're converted into this spectrogram representation, and we actually have it at 4 different timescales, so that glitches that are very, very quick, you can see in detail. Glitches that last a little bit longer, you can see the detail. When the detectors are operating, we add them daily. Currently, the detectors are down for reconstruction, adding new features, and should be running again in the summer, next summer. Once we have the glitches in a form, we put them through the machine learning model, and the machine learning model is, fairly standard, a deep learning convolutional neural net. And the model, like many machine learning models, basically spits out probabilities, what glitch is more or less likely. And we use those to then send the glitches into two different processes based on how confident the machine is. So glitches that the machine is extremely confident about, we just need to have verified. I think actually one of the earlier speakers mentioned that process. And then glitches that are sort of intermediate get sent to intermediates. And then the ones that are very, very uncertain, where there's absolutely no consensus from the machine about what it is, are potentially new classes of glitch. So that's something actually which is distinctive about our setting, is that it is likely that there are things that have not been seen ever, and that the volunteers can help identify. In contrast with something like Snapshot Serengeti, it's, you wouldn't expect that in a camera trap you would discover a new species of something. Part of the way that the validation works is the leveling that was mentioned earlier that we do. So if you are a beginner and you go to the site, you're given just two kinds of glitches, or rather, you're given glitches that the machine learning has predicted with high confidence to be one of two types, blip and whistle, which are very, very distinctive. But because the human is basically verifying that the machine got it right, there's also this none of the above option where the human volunteer can say, that that's not a blip or a whistle. And in fact, at one point, there was a new kind of glitch that the machine hadn't seen before, and it was very, very confidently classifying it as whistle. So the volunteers were able to contribute just by saying, basically the machine got it wrong, even though it is very confident. This also helps with training. Once you can do this task with just the two, you are advanced to a second workflow where there are 5 glitches plus none of the above, then to a third one where there are 9 plus none of the above, and eventually to a workflow where you have all the glitches. We actually did some experiments with this, and we're able to show that having those levels of training did help with accuracy. People who'd gotten it were quite a bit more accurate, and also with retention, that people stayed longer in the project. Actually, someone asked a question about that earlier, and it is worth noting that the distributions here are extremely skewed. So the most active volunteers have done tens of thousands of classifications. The median number of classifications is like 1 or 2 because people try it out, figure out what the project's about, and then more than half of them decide that it's not for them. Once it's classified, it goes back into our, we retire it, it goes into the gold standard data, and it goes back to LIGO, where they can actually, we gave them a database access, they can search for glitches of a particular kind. And it's been very gratifying that a number of the investigations of the glitches basically are citing gravity spy as the source for the data that they're using. So that's been nice to see. Yeah, so you can do a search and, for example, get a list of all the blips. As I mentioned, there's a bunch where the machine learning has no idea what it is. And so there's an additional phase towards the end where the volunteers or the machine learning can try to sort through these unclassifiable glitches to see if there's a new glitch class that can be identified. And in fact, the volunteers very early on in the project identified several new ones. This is the one I mentioned, 1400 ripple, that the machine thought was a whistle. The paired doves people got excited about because they actually resemble the chirps that you get from black holes. So there was a lot of concern that this kind of glitch could actually be messing up their searches for astrophysics. And with a little bit more investigation, they were able to, the LIGO scientists were able to try to identify what the cause was. And in fact, actually, we have just gotten word that we're likely to be getting continuing funding for our project. And what we want to do in the next phase is to actually let the volunteers do the same kind of legwork that the LIGO scientists currently do, taking a new kind of glitch and actually trying to identify what the cause is. There's also been some work looking at the machine learning to try to identify new glitches by doing sort of an unsupervised clustering. And it's been interesting that the process that the volunteers go through is actually very communal. That someone will identify something. There's this sort of very interesting distributed process of tagging where people use the talk feature on a particular object to apply a tag, and then amongst the more active volunteers, active discussion about what the boundaries of this new class should be, actual searches to look for additional examples. Kind of in contrast to the previous talk, we have at least one volunteer who claims to have a photographic memory, and so we'll actually say things like, I just remember all of the glitches I've ever looked at, and that way I can tell when I've got a new one that which ones it's similar to. Obviously, that's an extremely rare talent. Most of the time, the volunteers are happy to have a little technology support. But it's been interesting for us, you know, looking at the social nature of the interaction and thinking about how to try to support that better. Things that I think are interesting about the project that could be a takeaway. So it is, I think, very different in the sense that it's not oriented around data collection, but rather around classification. But I think that in a sense, those are complementary in the sense that you know, having a lot of data collected is important, and then being able to make sense of it as the next phase is also important, and that in a sense that opens up more opportunities for participation. The other thing I think that's interesting is the complementarity of the human and the machine capabilities, which has come up several times. And in particular, the idea that if the machine is very confident about something, that means that it's possibly something that, you know, the humans don't have to spend as much effort on. And then on the flip side, places where the machine is extremely unconfident suggests either the need for human annotation, which has been mentioned, or the possibility of a new discovery, which is, like I said, maybe not what you'd expect with animal species, but certainly something that comes up in a lot of settings. And so with that, I will conclude, and hopefully there's time for a question or two.
Thank you very much. Questions from here? Anybody? Offer has a question.
Thank you, Kevin, for this great talk. I have a question about the discoveries, the last part of your presentation, and you mentioned that this might be less relevant for species identification, but I'm not sure that is the case. And I'm part of this community of volunteers, the local community that reports by naturalists, and we encounter cases where they're not sure. And for example, whether this is a dog or a jackal, wild dog or a jackal, and it might be a hybrid, right? So no machine would be classified to identify these hybrids. So I think this is relevant, and I can see how the community-based process would be very effective in identifying such new classes. But I think that in your slide you showed both community and the AI take part in identifying the classes. So I'm not sure how the AI could contribute to identifying discoveries of new classes.
So the AI doesn't do it by itself, obviously. It's being used to support people who are doing research on the glitches. But the basic idea is that the convolutional neural net is essentially doing a feature extraction from the glitches. And so what you can do is, you know, instead of going to the end and having it tell you which glitch it thinks it is, you can take an intermediate point as a feature extraction, and then you can do an unsupervised clustering based on those features, and get a map like the one that I showed, where you identify glitches that are close together in this feature space from the net. So we use that in the similarity search, which I didn't go into a lot of detail, but if a volunteer has an image they're interested in that they think is potentially of a new type, they can search for other glitches that are similar to it. And that similarity assessment is done in this feature space that the CNN is extracting. And then you can also just take all of the glitches that are none of the above and do the same kind of bottom-up unsupervised clustering of those, and look for ones that are close together in that space.
Any other questions from here? Maybe Tanya. There she is.
Hi, Kevin.
Hey, how are you doing?
It's interesting to say hello to you from Israel. So, you know, the one of the characteristic or unique aspect of a lot of scientific citizen science projects is that the data come from much more uniform data sources. You know, if we're talking about the typical sky surveys, the data sources are much more uniform than something in, you know, biodiversity related, wildlife related data sources. So what of the workflow and the assumptions in the citizens, in structuring citizen science projects translates to a bigger diversity of data sources, and what should we be aware of in general? And how can we?
Yeah, so that.
I'll stop there.
Right. Yep. That is an excellent observation. That you know, even though the glitches are quite diverse, the process that generates them is uniform, and they all end up, you know, centered and so on and so forth. Having said that, though, the work that you and your colleagues have done does suggest that even with a diversity of you know, images that are coming in, that it's often possible to extract the pieces that you're interested in and do some kind of machine learning on them that can adapt to the diversity that you're seeing. It actually reminds me of one, and I think something that illustrates what you're talking about very nicely is an important feature in a lot of neural nets is something that gives you a certain amount of location independence. Because, you know, if you're looking for a dog in an image, it doesn't matter whether the dog is in the lower corner or the upper corner, right? It's still a dog. In our case, if you're in the lower corner, you're at a low frequency, and if you're in the upper corner, you're at a high frequency, and it actually does make a lot of difference. And so, in fact, we want models without location independence, which was not, I think the machine learning person, you know, that was one of the things. It's like, well, of course we want location independence. It's like, no, don't need that. So, so I think that's an illustration of the way that the specificity around the images is actually going to have to influence the way that the AI is developed. But you know, even so, I think, for example, if you looked at the snapshots Serengeti interface, which I'm more familiar with, right now when you start, there's like 54 different species to look at. And some of them are actually quite subtle, the distinction between different kinds of gazelles, for example. So I think if, you know, if I were put in charge of redesigning it, starting off with that leveling approach, I think would be useful, so that someone shows up and it's like, you know, lion, giraffe, elephant, where basically, you know, they're such familiar animals that you don't even need to look at the training. And they're so distinctive that you could just glance at an image, get it right away. And then, you know, add in additional animals more gradually, so as to be essentially training the volunteers at the same time that they're contributing to the project. And I think that would work as well with camera trap data, which are, as you said, very diverse, as it would with the kind of images that we're dealing with.
Another question from Elon.
Yes. Hi. You said that currently the sensors are not working because they're redoing them or something, right? Now the question is, yes, when they come back online, what do you have to do in order to get your system working again? Because there might be some real differences in the images or something. Is that true?
Yeah, you know, it's an important point that that part of the reason for the project is exactly that the detector is not static, that as it is being worked on, hopefully certain kinds of glitches are getting fixed and they don't occur anymore, and other kinds of glitches may be being introduced. And so part of what's been happening, it's actually the observing run that just finished. It actually ended early because of COVID. They were having troubles with staffing. That was observing run 3. And there are things that just don't show up in observing run 3 data and that we actually took out of the interface. And then part of the challenge for the volunteers is identifying the new things that have gotten added. And so one of the things we had to do was to make sure that the volunteers knew which part of the data, what the time frame was that the data came from, because if you're looking for new kinds of glitches, you wouldn't want to be looking at the old data because first of all, it's not relevant anymore. But secondly, the detector has changed since the original run. You would want to be looking at the 03 run. And so when we start 04, there is going to have to be that sort of period of saying, we know for sure that this glitch got fixed, take it out, and to let the volunteers know that they should be, recalibrating what they're looking for in terms of the new data. It also is the case that each of the detectors is a little bit different. So LIGO, Hanford, and Livingston are not identical designs. They're very, very similar, but they're not identical. And so they actually have slightly different glitches. So again, the volunteers are told that this is data from Livingston. And then Virgo, which is the European one, is totally different. It's, it's a different design. It's actually 3 kilometers on a side. And one of the challenges of putting Virgo data into the system was, it had to have its own level with its own choices, but it was actually, we had to get examples of the kind of glitches that the Virgo people thought were important to populate the menu. So there is actually the sort of interesting adaptation process. So again, that might be something a little bit unique to the kind of manufactured system that we're looking at. But I think, there are echoes of that in all of the kind of customization that has to happen for the different species that the identification algorithms have to be trained for. So, but yes, good observation.
Okay, so I think we have no more question, and this ends our talk.